Yeah, so we have seen that about the electric field, that is what is electric field, and we have also seen that how what is the value of electric field for a point charge, that is kq by r square, that is the electric field only. And this electric field, whenever it asks to calculate the electric field at any point, I have told you just keep a 1 coulomb of charge and calculate the basically force between these two charges. That is going to be the our electric field only. So this is how we have learned the things. Now let us proceed further. So basically, if I ask you electric field due to a point charges, what is the electric field due to a point charge? Electric field due to a point charge is, for example, there is a point charge q is there, and at a distance r I want to find the electric field at this point. So I have told you, you have to keep a 1 coulomb of charge here, and you have to calculate the force. The force will be k q 1 coulomb divided by r square, and this is equal to k q by r square, and this is the electric field. This units will be Newton per coulomb. This is what we have seen in the yesterday's class. Now our next topic is, from here after this you have to remember the electric field due to the point charge. Our next important topic is vectors form of electric field. As we have seen the vector form of Coulomb's law, similarly we have a vector form of electric field also. Form of electric field. So if suppose there is a charge is there, okay, and at some distance r I want to find the electric field at this point, then in a vector form, then my electric field, okay, will be written as, see, this is the magnitude kq by r square, this is a magnitude. I want to write the direction, so I have to multiply it by the unit vector r cap. So this will be equal to kq y mod of rq into r vector. So this is the vector form of electric field. Remember that you have to put q with sign. You have to consider sign also. Whenever there is a vector form, you have to put the values with sign. This is an electric field due to a point charge at a some distance r in a vector form. Okay, that is about the electric field in a vector form. So we have seen for a point charge, the electric field is kq by r square, and in a vector form, it is kq r vector by mod of rq. Clear? Now let us start with the some important things, because this is about the electric field we know. But before solving any question, it is very important to know about the properties of electric field lines. So what are the properties of electric field lines? Properties of electric field lines. That is very important properties we have to, because every time one question is there with the properties of electric field lines, so you should know these properties because they are very important. So let us start with the first property. The first property of electric field line is electric field lines always originate from the positive charge and always terminate toward the negative charge. You can say electric field lines always originate from a positive charge and goes to infinity. If my negative charge is not present there, it will goes to infinity. So our first property is that the field lines are always originate from a positive charge. Okay, so the electric field lines, okay, the electric field lines always 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 originate from positive charge and go to infinity Okay, that is about the properties of electric field line. First property, that means suppose there is a positive charge, plus q is there, then the electric field line due to this plus q will be like this. Okay, the electric field line will be like this. From positive charge it will originate and it will go to infinity. Okay, it will go to infinity like this. This is the electric field lines due to a positive charge like this. Okay, like this, it will go to infinity. This is about the first property of electric field lines. Okay, next property is, what is the next property? electric field lines originate from infinity and terminate to the negative charge. The electric field lines the electric field lines come from infinity, comes from infinity and go to negative charge. Okay, electric field lines come from infinity and go to negative charge. For example, suppose there is a negative charge is there, then the electric field lines will be coming from infinities and it will enter into the negative charge like this. Okay, like this, like this, like this, like this, like this. So it is something like this. Okay, this is the second property of a electric field line. Third property is, what is the third property of electric field lines? Third property of electric field lines, that is, suppose there is an electric field line is there. Okay, if you draw the tangent to the any point on the electric field line, it will point out the net electric field at that point. Okay, so the tangent to the electric field lines denote the net electric field at that point. For example, what I'm trying to say, suppose this is my electric field line. Okay, suppose this is my electric field line. And at this point, I want to find the net electric field. So what I will do, I will draw a tangent at this point. Okay, I will draw the tangent at this point. I will draw a tangent at this point. 1 minute. Yeah, like this. I will draw a tangent at this point like this. So this is my tangent at this point, will donate the electric field, will donate the electric field at this point. Okay, okay, like this. So this is the electric field will be donated at this point. So at this point, the net electric field at this direction. At this point, if I ask you at this point, you will draw a tangent, the net electric field will be in this direction like this. So that is the third property of electric field lines. What is the fourth property? Fourth property, electric field lines never intersect each other. Electric field lines never intersect each other. The electric field lines, okay, never intersect each other. Never intersect each other. What I am trying to say, suppose there is a one electric field line like this, and suppose I'm changing the color, but it is not changing. Suppose there is a one electric field line, this other electric field line like this. This is a one electric field line. This is another electric field line. What I am trying to say, and they will not intersect each other. Why? Why it is like this? They won't intersect each other. What is the reason? Because suppose they intersect, they will intersect at this point, right? This is a point of intersection. Suppose this is a point of intersection. Now at this point, draw a tangent. If you draw a tangent, you will get that this electric field line will say the direction at this point is this. And this electric field line will say the direction at this point is this. So at one point, you are getting two directions of electric field line, right? Which is not possible. We are getting two directions of electric field line, which is not possible. Hence, at same point, we have we have two directions of electric field lines, which is not possible. Which is not possible. Which is not possible. Okay, that is why the electric field lines can never intersect each other. Next thing, the electric field lines will never form a closed loop. Okay, the electric field lines will never form a closed loop. Remember that the electric field lines will never form a closed loop. Electric field lines will never form a closed loop. That is another property of a electric field line. That is fifth property. Electric field lines will never form a closed loop. Means you never see electric field line forming a loop like this. Like what I'm trying to say, you will never see the electric field line is like this. It never form a closed loop. Okay, it never exists in closed loop. This is not possible. This is not possible. Why? Why not possible? Because electric field lines is a conservative force. Is a conservative force. So for conservative force, that is why it is not forming a closed loop. Okay. Second property is that is electric field lines is directly proportional to the magnitude of the charges. Okay, electric field lines directly proportional to the magnitude directly proportional to the magnitude of the charges. For example, let me try to explain you. So suppose there is a one charge of plus 2q and there is another charge of plus 5q, and we have seen the electric field lines diagram for both the charges. So what you will observe, from plus 2q 1 2 3 4 5 6 7 8. 8 lines are there, but plus 5, what you have seen, 1 2 3 4 5 6 7 8 9 10. So here the number of electric field lines are more, right? So that means the charge is more. Okay, if the number of electric field lines are more, that means the charge is more. So that is what is the another property of an electric field line. So more number of charges, that means more electric field lines will be there. So that's why the electric field lines is directly proportional to the magnitude of the charge. If suppose some charge has a more magnitude, that means it has a more electric field lines also, and if it has a more electric field line, that means more magnitude also. You can directly say like that. Okay, now seventh property is that electric field lines will be all will like electric field lines is always, you can say like this, suppose I have a suppose I have an electric field line like this. Okay, this is my electric field lines. Okay, this is my electric field line. If I calculate the electric field, suppose this is my point A and this is my point B. electric field at point A, electric field, and suppose I calculate the electric field at point B. Now you tell me, electric field at point, what is the relation between electric field and point A at point B? Whether it is greater than A, whether electric field at A is less than B, what is that? Or whether electric field A is equal to electric field of B. Which one is correct? Which one is correct? In first, second, third, which one is correct? Which one is correct? Electric field at,
First one.
sorry? Which one is correct? Electric field at A greater than B, yeah, B less greater than A, or A equal to B? Which one is correct?
Electric field A greater than B.
What? Okay, yes. Why? Because what is the reason? Electric field at A is greater than B. What is the reason? The reason is very simple. You can say strength of electric field, strength of electric field is directly proportional to the density of lines. Density of lines. You can see the density of line in this region is more, right? The density of line in this region is more, right? It has a more density. Okay, it is more dense, it is less dense. So here the strength will be more, here the strength will be less. That is a another property of a electric field lines. Okay, so density is directly proportional to the strength of the electric field line. Clear? So these are the important properties of a electric field line. There is one more property is there, but I used to teach that property when I teach you conductors, but you can note it here. Electric field lines are always perpendicular to the surface of conductor, but I will tell you the reason and proper explanation for this when I will teach you the conductors. Perpendicular to the surface of the conductors. Reason will be given when I teach you conductors before starting the capacitors, because before starting capacitor you should have all the knowledge about the conductors. Okay, so these are the different properties of a electric field line. Let us see some electric field lines diagrams. Let us see some diagrams of electric field lines. Okay, suppose I want to represent a uniform electric field line. Suppose I want to draw the uniform electric field lines. How will I draw? How will I draw a uniform electric field line? So for drawing the uniform electric field lines, you have to draw the parallel lines. This parallel line, parallel equidistance lines. Remember, parallel equidistance line represent the uniform electric field. This represent a uniform electric field. Uniform electric field. What do you mean by uniform electric field? Suppose I calculate the electric field at this point and I calculated electric field at some other point. So what I'm trying to say, electric field at A will be equal to electric field at B, or any point you can take. Suppose this point I take electric field at C, so it will be also equal to electric field at C also. Means you can take any point, it doesn't matter. You can take any point, it doesn't matter. Okay, electric field at A is equal to electric field at B is equal to electric field at C. This will be all same. Clear? So uniform electric field lines will be represented by the parallel equidistance line. This is called as a parallel, okay, parallel equidistant lines. Okay, this is represented by the parallel equidistance line. Second, I give you one configuration. Try to draw the electric field line diagram for this. Suppose this is plus Q and this is minus Q. Can you draw the diagram for this plus Q and minus Q? How will be the electric field lines diagram draw? Look for this configuration. Can you draw? How the electric field lines will look for this?
Minus Q to plus Q.
Yeah, the electric field lines will go from not plus q to minus q, no? Not minus q to plus q, because electric field lines originate from positive charge, enter into the negative charge. So it will be something like this, from plus q to minus q, right? Like this. Okay, it will be, so it will enter into the negative charge. Okay, and here it will originate from the positive charge. Okay, so this is the electric field lines due to the a dipole. You can say it is a dipole na. If you see properly, it is a dipole, because positive and negative charge are there, they are separated by a small distance. So this is a dipole basically. This is, we will study what is dipole also, but right now you can see the electric field line diagram for a dipole will be look like this. Okay, this is a dipole. If suppose I give you this configuration, uh, suppose there is a plus q, and there is also a 1 plus q is also there. Now can you draw the electric field lines for these two charges? Plus q and plus q is there. Okay, there is a two charges, they have a plus q and plus q charge. It is now, it is not minus q. Then what will be the electric field lines look like? How it will be look like? Everyone draw in their notebook. Everyone draw in their notebook, and when I draw, just verify it. How it will be look like? How it will be look like? How the electric field lines for this configuration will look? If you draw, there, see, there for positive charge, we know that the electric field lines originate from the positive charge and go to infinity, right? We know this. So it will something like this, because they are positive charge, so they will repel each other, right? So it will be something like this. It will be something like this. Similarly here also, like this. So you can see it is not looking perfect, but like it will be something like this only. We can verify with the internet also. You can search, there are a lot of different diagrams are there. So this is something like this, means electric field lines are going and touching at infinity. They will touch at infinity. Okay, they will touch at infinity. You can see they are becoming almost parallel. Okay, almost parallel. So parallel lines are touched at infinity, right? Are you getting my point? So this is the how you can draw the electric field line diagrams for the different types of geometry. Now there is a one problem which has been asked in the previous year question. Just try to answer it. Which electric field line diagram is correct? And the configuration they have given is that the similar charges are placed on the equilateral triangle. Okay, this is the configuration is given, and they have given the different types of electric field lines diagram. Okay, let us what are the diagrams they have given? That is the first diagram they have given. This is the first diagram. Second diagram they have given is this. This is the second diagram. Third diagram. Yeah, third diagram is like this. And fourth is none of this. So you have to pick which is the correct diagram for a triangle for the charges placed on the equilateral triangle. Obviously, they are placed on the corners. So basically, you have to tell which diagram is correct. This is a previous year question. Okay, you have to pick which option is correct. One, two, three, four. Which option is a correct option? Which option is correct?
One.
One. See, it is a similar charges. Similar charges means they can be either positive or either negative, right? Either positive. Just try to understand. They can be either all charges will be positive or either all charges will be negative. Now you think which one is correct? Just use all the properties which I have told you. Just apply all the properties. Just you will answer it very easily. It's a very easy question. That time, this is one of the easiest question. If you remember all the properties, you can just answer it. What is a property? It is a similar, see, first try to analyze the first picture. In first picture, what is given? It is a similar charge, right? Similar charge means either all charges will be positive, okay? Either all charges will be positive or either all charges will be negative. This can be one the possibility, right? Okay, so you can find answer any one of them, you will get the correct answer only. So let us, I am considering positive one. If you consider positive one, just try come here and see. If it is positive, the charge will, or for a positive charge, what is the property? The electric field lines always originate toward the from the positive charge and goes to infinity. That is a property, right? Now let us come here and see. Electric field lines are originating from the positive charge, right? But is it going to infinity? No, it is going inside the another positive charge. See, this is going inside another positive charge. Is it possible? Is it possible?
No, sir.
Yeah, so that means this diagram is wrong. And if you consider negative also, suppose you consider negative, no sir, I will consider negative. Then for the negative charge, what is the property? Electric field lines originate from infinity and go into the charge, right? It will go inside the negative charge. See, for this, it should go inside the charge, na? But it is going away from the charge. This arrow is away from the charge. Again, it is wrong. So whether you take positive and negative, in both the case, this electric field lines is wrong. See, we have seen there, na? If there is two positive charge, obviously these electric field lines will repel each other, right? Because they are the same charge, they will never intersect. We know that. Okay, so that means this diagram is wrong, because if it is a positive charge, it has to go to infinity. Second thing, if it is a negative charge, then the electric field line should enter inside it, but it is going away from it. So that means they both the cases, this diagram is wrong. So we cannot choose this option. If you know the property, you can solve it. Now come to here. One of the property of electric field line is that they never form a closed loop. They never form a closed loop. See here, you can see properly, they are forming a closed loop, right? They are forming a closed loop. So that means this diagram is automatically wrong. Now just come here. Is this is correct? If you see, the electric field lines are given there, they are not intersecting each other, they are not forming a closed loop, they are fulfilling all the properties, the no property is getting violated here. So that means this can be the possible correct option. Simple, this can be the possible correct option. None of these, obviously this will won't be correct. So this is the correct option for this. See, simply you have to apply the property. Simple. Nothing is there. If you are applying the property simply, you will get the correct answer. Let us take one more example. Suppose there is charge Q1, there is another charge Q2. Okay. And this is the electric field lines we have. Electric field lines diagrams we have. Oh, sorry. Why it changes the color? Oh, sorry. I have to draw something else. My question is that, sorry, my question is that first thing you have to tell Q1 is in magnitude wise, Q1 is less than Q2. Sorry, Q1 is greater than Q2. Third, Q1 is negative and Q2 is positive. Fourth, Q1 is positive and Q2 is negative. Yeah, it is a multiple correct. More than one option will be correct. So you have to comment on Q1 and Q2. Comment on Q1 and Q2. Sorry. Comment on Q1 and Q2. You have to give the comment on Q1 and Q2. Comment it.
Q1 is positive and Q2 is negative.
Okay, Q1 is positive, Q2 is negative. Next. Whose magnitude is greater? Which has a greater magnitude?
Q1.
Why? Why Q1 has a greater magnitude? Why Q1 magnitude is greater?
Electric fields are more than Q2.
Simple, you can see the electric field lines from Q1 is more, right? We have told that one property. There is a one property is there. Electric field lines directly proportional to the magnitude of charge. More magnitude, more electric field lines. Less magnitude, less electric field lines. Simple. So you can see here the electric field lines for this charge is 1, 2, 3, 4, 5, 6. 6 electric field lines. Now come to this charge. 1, 2, 3, 4. 4 electric field lines. So Q1 magnitude is greater than Q2 magnitude. Simple. Because it has more electric field lines. So more charge. It has less electric field lines, less charge. And what about the sign? How I predicted the sign? How you predicted? See, electric field lines is going to infinity, right? It is originating from a charge and it is going away. So this will be positive. It is going inside. So this will be negative. Simple. Is it clear?
Yes, sir.
Yeah. So this is how you have to. These are the different properties. See, if you remember the properties, you can solve all the problems on electric field lines. Okay. 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 So we have seen the properties of electric field lines. Let us move to the next thing, which is very important. That is discussion on constant electric field. Sorry, what happened? 1 minute. Yes, discussion on constant electric field. Let us discuss about the constant electric field. See, constant, or you can say uniform electric field is represented by constant uniform electric field is represented by how it is represented? How we represent a constant and uniform electric field? By a parallel lines, right? By equidistant parallel lines are there, that is used to represent the electric field. Okay, the electric field is E naught. Now, if my electric field is constant, it is constant, right? Because it is represented by a uniform equidistance line. So what is my force? My force is defined as Q into E. Okay, E naught. So E naught is constant. E naught is constant. So obviously my force will be also constant. This is also constant, right? If my electric field is constant, then my force will be also constant. And if the force is constant, if it is constant, I know force is what? Mass into acceleration. So this will be equal to Q into E naught, right? So my acceleration will be equal to Q E naught upon M, right? So I can say one thing. My electric field is constant, so my acceleration is going to be what? My acceleration is also going to be constant, right? It is a constant acceleration. And whenever there is a constant acceleration, what will be the path? Now, what is the path? What is the path of the particle in constant acceleration? In constant acceleration. So can you tell me about the path of the particle? If I throw a particle, if I keep a particle in a constant acceleration, then what will be the path? This is a question not from the electrostatic. This is a question of a basic kinematics. I'm asking a basic kinematic question. See, we have considered a constant electric field, so our force will be constant. If the force is constant, we know that acceleration will be going to be constant, right? Now my question is very simple. If it is a constant acceleration, then what will be the path of the particle? What could be the path of the particle? What are the possible path it can have? That is my simple question. See, what will be the path? What can be the path? If my acceleration is constant, what will be the path of the particle? See one thing. This is a not from electrostatic. This is a general physics idea I am giving you. Whenever the acceleration is constant, okay, there is only two paths are possible. Two type of path will be there. Either parabolic path, okay, that is projectile you have seen, or either it will be a straight line. There is no other path will be possible. This is the only two path will exist. When it will be straight line, when my velocity is parallel or anti-parallel to the acceleration. Do you understand what is the meaning of parallel and anti-parallel? Everyone understand what is the meaning of parallel or anti-parallel? Okay.
Yes, sir.
If my velocity is parallel or anti-parallel to the acceleration, then it will be a straight line. Otherwise, it will be a projectile. Simple. Otherwise, it will be a projectile. It will be always be a projectile motion. So it is very clear for me that whenever there is a question come, okay, why I have told you this thing? Because see, whenever the question come, because physics is all about concept. Now, if my question is came and it is a question on a constant electric field, then I am very sure that there will be only two paths will be there. Either it will be a straight line path or either it will be a projectile, right? So only two paths will be possible. So I have to, now this much is only the electrostat. After that, you have to apply the basic kinematics. There is no electrostatics will be there. Let me show you one question also. Let me ask you one question, then it will be very clear to you. Okay, let me ask you one question. I have this question, or is simply let me before asking a question, let me draw this. So there are the two cases we have seen. Two cases will be there. What are the two cases? Case number one. Suppose I have a uniform electric field line. Okay, uniform electric field line like this. Uniform electric field lines are there, and I have taken a charge Q having mass m, and I have thrown in a straight line. Okay, this is a velocity. This is a velocity v, and the electric field E naught is there. Then in this case, In this case, my path will be, what is the path? Path is a straight line, simple. Why? Because you can see my velocity is parallel to the acceleration, right? Because see, electric field is this direction, so my acceleration will be also in this direction, right? Because we know what is because the direction of acceleration and direction of force will be same, right? Because why the direction of acceleration and direction of force will be same? Because see, force is what? Force vector is equal to q into e vector. So you can see both the vectors are in same direction, right? So on positive charge, the electric field, the force is along the direction of electric field. On negative charge, it is opposite to the direction of electric field. So force is equal to q into e, and my acceleration will be is equal to qe vector by m. So you can see the direction of acceleration is acceleration direction of acceleration same as electric field, right? So this is the case one, okay? But suppose if I take another case two. In case two, what I am doing, I'm doing a small change. Okay, I'm doing a small change. What is a small change? Case two. In spite of doing like this, I am throwing the particle like this. Okay, this is my charge q, mass m, and I'm throwing it as a velocity v with a theta angle from the horizontal. Then in that case, my path is going to be projectile, because my velocity and acceleration, see, my acceleration will be like this, okay, and my velocity, they have an angle of theta. Here the path is projectile because it has an angle of theta. So if it is a projectile, I can ask you anything, right? Now I can ask you anything. What I can ask? See, there is a two components will be there of velocity. One is, there is a two components of velocity will be there. You can see one in this direction, and another one is, sorry, another one is this direction. That is v cos theta, and this is v sin theta. Now I can ask you anything. Okay. See, what is the, if it is in vertical directions, there will be what are the forces will be acting on this? Let us try to check what are the forces will be acting on it. See, this charge is moving like this. Okay, this charge is going like this. It is going like this, and this is an electric field. This is a electric field. So what is the my question is that, or let me draw it another way. It's not looking correct because, 1 minute, just give me 1 second. Okay. Okay. Yes. So suppose this is my positive plate, positive charge plate. This is a negative charge plate. So my electric field lines will be like this. This is my electric field lines from positive to negative. The electric field lines will be like this. Okay, from positive to negative. This is my electric field lines, right? What I did, I have taken a positive charge. Okay, I have taken a, suppose this is my horizontal. I have taken a positive charge and throw at an angle of theta. So the path will be like this. Okay, this is my velocity v at an angle of theta from the horizontal. This is charge q and mass m. Right? I have thrown it. Okay, so you can see in this direction we have a QE by m force will be there. Okay, sorry, force not, acceleration will be there in this direction, because the charge, there will be force acting in this direction q into e, right? So acceleration will be QE by M. That is the acceleration here. And also the gravity will also act. G will be also there. So if I ask you what is the net acceleration? What is the net acceleration? What is the net acceleration? Because there are the two four accelerations will be there. What is the net acceleration? So net acceleration will be QE by M plus G. This is the net acceleration we have. So if I now I will ask anything to you. First thing, what is the maximum? What is sorry? What is the maximum height? Whatever the question you see in the projectile, the same question can be asked here. What is the maximum height? Maximum height will be what? When it reach the final velocity zero. So what? How you calculate? You calculate u v square sine square theta by 2g. That is a. But here we have to write g net. G net is what? G net will be v square sine square theta by 2 times of g net is what? G net is QE by M plus G. This is my G net. Okay, net acceleration. Second, I can ask you range also. What is range? Range is what? What is range? How you calculate the range? Range is u cos theta into time of flight. Time of flight. What is the time of flight? How much is the time of flight? Time of flight is 2 u sine theta by G, right? But G at a place of G, you have to write G net. So you will get time of flight at how much? U square sine 2 theta by G net. That is how much? How much it is? U square sine 2 theta by QE by M plus G. Right? So just you can see we are just replacing the G in the formula of per projectile by G net. G net is nothing, just the total net acceleration. Second, I can ask you what is the other thing is left. I think everything is covered. Maximum height, range, and anything else. Time of flight. Yeah, time of flight. You can also write time of flight. Time of flight. Time of flight is how much? You will get that is 2u sine theta by G net. So what is G net? G net is 2u sine theta by QE by M plus G. So this is the different questions can be asked if it is given in the projectile. So now I hope you are confident with everything. Okay, just what you have to do, whatever the thing you have learned, just replace G by G effective, or you can say G net. This is also called as a G effective also. G effective or G net. Okay, G net, whatever you can say. So let us take one example. I hope you will understand this example. Suppose okay, suppose there is a electric field lines are there. It is a uniform electric field. Okay, it is a uniform electric field. One more thing, how to calculate the G effective or G net? See, G effective is equal to force at equilibrium, okay, divided by mass. Means you have to calculate the force at equilibrium, or you can say mean position, and then you have to divide it by mass. You have to divide it by mass. Equilibrium, or you can say mean position. Let me write it both so that it will be easier for you to understand. Okay. Force G effective is force at equilibrium, or you can see mean position. That is divided by mass will be the G effective. So what I am trying to say, suppose this is an example. We have a let me draw the electric field lines. This is a uniform electric field lines are there. Okay. Uniform electric field lines are there. And I have given you a I have given you one pendulum. Okay. Suppose this is my pendulum, this having a charge Q and mass M. I keep it in the electric field. Then my question is, uh, what is the time period? What is time period of the pendulum? Can you tell me what is the time period of the pendulum? See, basically what you have to do, you have to replace G by G effective. That is a simple thing you have to do everywhere. Just replace, if it is a constant electric field, you have to replace G by G effective. And how to calculate G effective? Calculate the, first you calculate the mean position. Where will be the mean position? After doing the mean position, you have to calculate the net force and divide it by mass. That is a simple approach, right? So just tell me, is there is any doubt till here? Till here, is it clear to everyone? Is it clear to everyone till here?
Yes, sir.
Are you able to get the point that how we have written all these formulas just by replacing G by G effective? Why we have added this? Because both the acceleration you can see in the same direction, right? QE by M is also act in the same direction, because the charge, the force will be act in this direction only, right? Because force is equal to Q into E, right? So for a positive charge, the force is along the direction of electric field. For negative charge, it is opposite to the direction of electric field. And electric field always go from positive to negative. That I have told you in the properties of electric field lines only. So this is my G effective or G net. So I have replaced in all the formulas, just I have replaced G net, G by G effective or G net. Similarly, here also I am asking you time period of the pendulum. See, if it is in if the electric field is, we know, if there is no electric field, we know what is the time period. That is 2 pi, t is equal to 2 pi by root over of L by G. This is the formula we know. But here there is an electric field is there. Suppose the electric field value is E. Okay, so we have to replace G by G effective, right? We have to just replace G by G effective, and now you have to find G effective. So my first question will be that, sir, where will be the mean position? See, obviously this has charge Q and this is placed in the electric field. So this will not stop here. The force will act in this direction, right? Because QE, force will act in this direction and it will try to bring the pendulum in somewhere here. So this will be going to be the mean position. It will be something like this, right? It will be something like this. This is going to be the mean position, right? Correct. Now you can see mg will act here, right? This is my mg, and there will be like this force, QE force, Q into E, that is Q into E force will act here. So what is my net force? My net force will be like this. This is my F net. So F net will be how much? Root over of, that is mg square plus QE square, right? This is my net force. So what is my G effective? My G effective will be whatever the force at the mean position, M into G whole square plus QE square divided by M. So you will get, this is equal to G square plus QE by M whole square. So that is my G effective here. Just put this value here, you will get the time period. So T is equal to 2 pi by root over of L divided by root over of, that is G square QE by M whole square. Simple. Simply you have done the calculation of G effective and you just replace it there. There is nothing is there. And how to calculate G effective? Calculate first, analyze the mean position, because there will be force in this direction. So obviously it will not stop here. It will stop somewhere here. At this point, what are the forces I have seen? I have calculated the F net. I have divided by mass. You will get the G effective. Just put the G effective here. You will get the total time period after putting into the electric field, right? Is it clear? Is it clear
Yes,
to
sir.
you? Okay, okay, okay. Let me, if you like, if you remember, There is a one very like famous question is there. Suppose I have a circle. Okay, I have a circular arc is or some circular path is there, and I hope you remember this question. There is a like one string. We keep one particle. We keep one particle, right? It has suppose it has a mass m, charge q, mass m. There is no electric field is there. If I have to move this particle into the circle, what is the minimum velocity we require? Anyone remember what is the minimum velocity we require to move this particle over in the circle, to make a complete circle? Suppose I take a thread, I put a one particle, and I want to make a complete circle like this. Okay, so what is the minimum velocity I will require? Anyone remember? Anyone who has completed class 11, they remember what is the minimum velocity we required? Anyone remember what is the minimum velocity we required here? Suppose this radius is r. What is the minimum velocity we require to complete this circle? Anyone remember?
No,
Okay.
sir.
The velocity we required is root 5 rg. This much is the velocity we required to complete this circle. If I want to complete the circle, I require this much velocity. Now suppose I am doing a small change in this question. It is the same question, but I am doing a small change. What is a small change I am putting? Suppose it is a same circle is there. Okay, this is a center. This is same charge q, mass m. Now same radius r is there. Now what I did, I have applied the electric field like this. This is my electric field, uniform electric field I have applied. Now you tell me what is the velocity we require. Now the question is what will be the velocity? If I have applied a uniform electric field E, uniform and constant electric field E, what will be the velocity? What will be the velocity? Now, if I replace it by a uniform electric field, if I just apply a uniform electric field now, then what will be the velocity? What you have to do? You have to calculate the G effective. What will be the G effective here? What will be the G effective here? What will be the G effective? Alright, this is the position, right? You can see G is acting downward and QE by M is also acting downward, right? This electric field line, see, the force on the positive charge is always along the direction of electric field line, and force on the negative charge is opposite to the direction of electric field line. This I have told you multiple times. So this electric field lines will apply the force in this direction, right? G is also acting in this direction. So total will be, what is the acceleration? A net will be there. What is G net? Simply, what is G net or G effective will be? What is G effective? G effective will be simple, G plus QE by M, right? G plus QE by M. This will be G effective. So what is my velocity then? Then velocity will be root over of 5 R into G plus QE by M. Simple. Simple. This is my velocity. Just you have to replace G by G effective. Are you able to understand what I am trying to say?
Yes, sir.
Simply, whenever there is a question of a constant electric field, remember you have to replace G by G effective. Nothing you have to do. There is no other thing is required to do anything. Just you have to replace G by G effective. There is no need to do anything. No need to do anything. Just replace G by G effective. Finish. Your question will be over. Just replace G by, if it is a constant electric field, if you have find out, okay, the electric field is constant, then you, whatever the question it will be, then it will be converted into a question of kinematics. It will no longer remain a question of electrostatic. You have to do nothing. Just you have to replace by G effective, because there is only two paths will be possible. Either it will be a straight line or either it will be a projectile. You know all the things about the projectile. Okay, if you have covered class 11th, if you don't know, I will teach you. But the thing is that you know everything about projectile. Okay, just replace G by G effective. And how to find G effective? Simple, I told you. Just you have to calculate the total force. Total force divided by mass. Okay, simple. And that is the G effective. After replacing, you will just whatever the formula you know, just replace G by G effective. You will get the all the questions. You can solve all the questions. Okay, that is a simple thing you have to do everywhere in all the type of question whatever you see. Now, now let's move to a see. We have seen electric field. We have seen electric field lines. We have seen the different questions on electric field lines, and we have seen also seen that. Okay, we have also seen the discussion of constant electric field. Now, our most important part from where from here we are going to start is the how to calculate the electric field due to the different types of geometries. Okay, there are the different types of cases. Suppose electric field line due to an infinite rod, electric field line due to a finite rod, electric field line due to a semi-finite length wire. Like these are the different cases are there. Electric field line due to the ring, electric field line due to the disk, due to the hollow sphere, due to the like different cases. We will see all these cases and we will understand all these concepts. So first example we will do electric field lines due to a rod. Okay, if you remember, we have solved one question, right? We have solved this question. We have taken a rod, we have given a positive charge to it, and it is lambda, sigma, or rho. What will be there for a rod? Lambda, sigma, or rho? What will be there? It will be lambda, sigma, or rho?
Lambda.
Lambda. So we have given lambda is there, and I have suppose, and we have also given the length. And what I told you, just at this point A, I ask you what is the force between these two. Now I am asking what will be the electric field at this point. What will be the electric field at this point? That is my question. Are you getting my question? My question is what will be the electric field here? What will be the electric field here? Can you calculate? What is the electric field? What we have to do? My first question is that what we will do to calculate that electric field? Can we apply the formula kq by r square? Is it applicable here? Is the formula kq by r square is applicable here? Is the formula kq by r square is applicable here? Answer is no. Why? Because this is a formula for a point charge, right? For a point charge, the electric field is kq by r square. This is a some distribution system. It is not kq by r square. And how to calculate the electric field? I told you, and I haven't given. I have also written also. You haven't even remember, then please remember it. I have told you what you have to do. Whenever they ask you to calculate the electric field at any point, just keep a charge of 1 coulomb at that point and calculate the force. Simple. You have to do the calculation of force only, but you have to keep a 1 coulomb charge. So what I will do, I will do smartly. I will keep a 1 coulomb charge. Now I will calculate the force between these two. So what is the now everything is same. Now if you remember, now it is become a same question. We have to go at a distance of x from here. We have to take a small element. This is what we have done earlier. This is dx. What is the charge on this? Dx dq will be is equal to lambda dx. That is what we have did. Then we have calculated a small force df, that is equal to k. Then we have a lambda dx. Then we have a 1 coulomb divided by x square. That is what we have to. And this is also equal to the small electric field also, because the force between the force on 1 coulomb charge is the same as the electric field. Then you will can say that my de is equal to k lambda into 1 coulomb. We will take outside dx upon x square. We have to integrate. What is the limit of integration? If you remember, we are integrating from x is equal to a plus l. That is our limit of integration. And then if you integrate, you will get k lambda, that is equal to 1 by a minus 1 upon a plus l, right? This is what we have, k lambda upon a into a plus l into l. So you can see my electric field at this point will be 1 by 4 pi epsilon naught into lambda into l divided by a plus l into a. This is the electric field we got. Simple. Did I do anything different? No, I just replaced q is equal to 1 coulomb. If you have remember the formula for this, what is the answer we got? What is the answer we got for this case? If we have calculated the force, right? What is the answer we have got? See, this is the formula, this is the answer we have got. Just replace q by 1 coulomb, you will get the same answer, this answer. And what the previously we have calculated is same. Just replace q by 1 coulomb in this. Just replace q by 1 coulomb and just match it here. Just come here. See, that we are getting the same value, k lambda upon 1 by a minus 1 upon a plus 1. Answer is same. So just what we have, whatever the question we have solved earlier, if you remember, in this same question, suppose in the same question, this question, where it is, yeah, this question, if I ask you what will be the electric field at this center, just replace q by 1 coulomb. This is the answer we got, right? Just replace q by 1 coulomb, it is the electric field at this point. Simple. Similarly, in the another question, in this question, I have asked you to calculate force, right, at this point. Just replace q by 1 coulomb, you will get the electric field. This is the electric field also. Just replace q by 1 coulomb, root 2 k lambda by r, and we will calculate and we will check also. You will get the same answer. What you have to do? Just replace q by 1 coulomb. Simple, simple. Just you have to do replace q by 1 coulomb. You will get the electric field at that point. That is a simple rule. You calculate the force, you just keep replace q by 1 coulomb. There is nothing new is there. Is it clear? Is it clear to everyone?
Yes, sir.
There is nothing new you are learning. You are learning the same thing. You are just applying the same integration and everything whatever we have seen earlier. Just we are replacing q by 1 coulomb. Simple. That is a simple thing we have done. Okay, so from tomorrow, like tomorrow morning session, we will start learning the electric field due to the different types of geometry, and we will see the, then we will move to the our third part of electrostat, that is called as a, after doing this calculation of electric field, tomorrow we will finish, mostly we will finish most of the calculation, and then we will move to the our next part of the electrostat, that is a Gauss law, which is a little difficult part. That is a student feel little difficulty in that part. We will cover each and everything in very detail. As you can see also, we are covering everything in very detail. We are going each and every concepts. Okay, no one, I haven't seen anyone taught this thing, discussion on electric field in a constant electric field. No one taught this thing, but I am covering this also, because in because there are the questions are there on a constant electric field. So if you are familiar with this topic, you can solve almost everything. Okay, yeah, so we will meet today in evening. Okay, and try to join the class. If you are leaving the class, that means it's it will affect your rank only. So today we will meet again by 5:30 to 7, and we are discussing in chemistry. So in chemistry we have discussed yesterday. Those who haven't joined the class, just go and see the lecture. We have covered in solid state different types of unit cells we have covered. Okay, we have almost finished all the types of unit cells, and today we are going for the calculations of packing efficiency and other things in a unit cell. So that calculation today we will do, and today we will meet, and today we will discuss about those calculations. So almost I guess in solid state we will need, I think, 2 or 3 classes. We will finish the solid state. Electrostat will go longer. I think most probably we can finish the electrostats by, because I will cover the potential and potential energy, everything within this chapter only. Because if you see the NCRT, in NCRT that potential and a potential energy and everything is in the capacitor chapter. It is in the different chapter, but we will cover everything will be here only. We will see the conductor properties and everything we will be here, because in capacitor we will take it as another chapter, and we will discuss the capacitor in very detail. Okay, beyond the NCRT, what is given in the NCRT, we have to go beyond that also, so that we can solve all the questions. Okay, and then we will move to the, first we will cover current and electricity, then we will move to the capacitors, because whatever the thing we have studied in current and electricity, the same thing will be come into the capacitor, just replace R by C. Okay, so that we will see. Till then, okay, thank you.